So my name is Jason Kalirai. I'm an astronomer at the Space Telescope Science Institute, STSCI. The Space Telescope Science Institute is one of the biggest astronomy departments in the world. We have about 500 staff members, about 100 of which are astronomers, including postdoctoral researchers. We also have some graduate students working on a wide range of problems in astrophysics today. It's a really exciting place to be because I get to tackle fundamental research problems that interest me, but at the same time, we get to build really big telescopes. And so one of the reasons I'm here right now in Austin is to highlight some of the science that we're going to be doing with the James Webb Space Telescope, which is the successor to the Hubble Space Telescope. In terms of my research, one of the problems in astronomy that really fascinates me is improving our understanding of how stars evolve. So we know, stars like the sun that are burning hydrogen into helium are in a state of hydrostatic equilibrium. They continue to generate heat and light for billions of years. And in the case of low-mass stars, it can even be trillions of years. So they burn their gas very slowly. And stars will spend the bulk of their time in that phase. And then as stars die, and they run out of that hydrogen, most stars will become white dwarfs. And white dwarfs are the stellar remnants of evolution for stars. And so these white dwarfs have no more nuclear energy, and so they will continue to radiate away whatever stored thermal energy is left in their ions, and they become dimmer and dimmer as time passes. So they just become cooler. They're like the cinders of stellar evolution. And so these are the two phases of stellar evolution that we understand pretty well. We know how stars burn hydrogen, and we know that stars will end their lives, most stars will end their lives as white dwarfs. The thing that we don't know very well is how stars get from one phase to the other, right? So what happens to stars as they go from being hydrogen-burning stars to white dwarfs? How long do they spend losing their mass and extinguishing that hydrogen before becoming white dwarfs? How much mass do they actually lose through those stellar evolutionary processes? And this is a field of astronomy that's very difficult to measure both observationally and predict theoretically. So observationally, when stars zip through these phases of stellar evolution, like the red giant branch and the horizontal branch and the asymptotic giant branch, they go through these phases very, very quickly. And so what this means is that it's very hard to catch stars in those phases and study them in detail. Theoretically, it's very hard to understand those phases because the processes by which stars lose mass depend on certain variables that we just don't understand that well. So for example, on the red giant branch, stars are going to start to lose mass through a wind. And the efficiency of that wind in driving away the envelope of the star depends on the opacity of the star, it depends on the gas to dust ratio, it depends on the envelope velocity of the star, and we just don't have good predictions of those quantities. On the asymptotic giant branch, the mass loss is driven by these complicated thermal pulses where different layers of the atmosphere and the core of the star is actually mixing. And you can get these dredge-up processes and increase the opacity and get more thermal pulses that drive away the mass. And again, the amount of mass loss that you get through those phases is sensitively dependent on the treatment of those thermal pulses. And we just don't understand that well. And so the technique that I like to use to measure the properties of stars in these phases is to take these white dwarf stars, which are the end products of all of these phases, and measure the detailed properties of those white dwarfs, and then try and connect those properties to the types of main sequence hydrogen burning stars that are making the white dwarfs. So these white dwarfs have remarkable properties. These are objects that are roughly the mass of the sun, but in a volume that's only about the size of the Earth. Okay? So the density of ordinary matter on the surface of these objects is about 1 million times greater than the density of ordinary matter here on Earth, or for example, the density of the sun. And so what this means is that the spectrum of these stars holds very important clues to the physical properties of the object. So the spectrum looks like an A-type star, which just has the hydrogen bomber line series, because the stars have a thin layer of hydrogen. But the bomber lines, instead of being 10 angstroms across, are 100 angstroms across. And you can model the shapes of those bomber lines to infer what the temperature of the star is, to infer what the gravity of the star is, and then you can get the mass of the star as well. And so these are very important stars because simply by measuring their spectrum, we can measure their masses. And mass is one of the most important parameters of stellar evolution. And so what I've been doing is looking for these stars that are members of star clusters. And so if we can look at a star cluster, we know that all of the stars in the star cluster formed at the same time, but some of the stars are still burning hydrogen, and some of the stars are already white dwarfs. The reason for that is that the white dwarfs represent the more massive stars that extinguished their nuclear fuel and became white dwarfs, and the hydrogen-burning stars are the lower mass stars that are still burning hydrogen. And so we can measure the masses of those white dwarfs, and because we know that we know what the age of the star cluster is, we know what the mass is of the star that's currently evolving from the main sequence turnoff to make a white dwarf. So you can use white dwarfs and star clusters to both get the final mass of stellar evolution and also the initial mass of the star that's evolving to make a white dwarf. So now you have this very important data point where you have both the initial mass and the final mass of the star at a given age. And so what I do is I exploit this technique in different star clusters that have different ages, right? So say I go to a star cluster that's 10 billion years old. In a time frame of 10 billion years, all stars that are more massive than about the mass of the sun have already extinguished their nuclear fuel and formed white dwarfs, right? So the data point that I would get from a 10 billion year old star cluster would tell me how much mass stars like the sun will lose through their evolution, low mass stars. But now say I go to a very young cluster, a cluster that's only 100 million years old. Well, in 100 million years, a star that's 5 times the mass of the sun hasn't had enough time to exhaust its hydrogen. So if I find a white dwarf in a star cluster that's 100 million years old, that white dwarf had to come from a star that was more massive than 5 solar masses. So I can put together a picture of how much mass different stars are losing as a function of their mass. And so we've constrained this relation called the initial to final mass relation, and it ends up impacting our knowledge of how those post-main sequence evolutionary phases are going to work.